Hello students, welcome to the digital classes. Let us continue with electricity. In the earlier classes, we have discussed electric current, which is defined as the amount of electric charge passing through a cross section in 1 second. In case of metal wires, the charges are free electrons. The formula for electric current is the amount of charge flown by time taken, which is equal to Q by T. The SI unit for electric current is ampere. Just like an object rolls down if there is difference in heights, electric charges move if there is potential difference. And to maintain a potential difference, we use a battery. A battery maintains potential difference across the wire. Here are some batteries of various voltages, and all of them will maintain a constant potential difference across the conductor. A battery supplies electrical energy by maintaining potential difference across the wire. Battery consists of two metal plates and a chemical which we call electrolyte. Based on the reactivity of the ions, there will be a chemical force that drives ions towards the electrodes, and with this the battery is able to maintain a constant potential difference. When we connect a conductor to a battery, the charged particles will start flowing in the wires, and thereby the appliance will work. The work done by the chemical force to move 1 coulomb of charge from the positive terminal to negative terminal is given by work done by charge, which is force times distance by charge. This we call electromotive force. Electromotive force is the work done by the chemical force to move 1 coulomb of charge from positive terminal to negative terminal. The symbol for a cell is given by one long line and a short line as shown in the figure. When we connect several cells, we call it a battery. Then we have learnt Ohm's law. The current in a conductor is directly proportional to the potential difference applied across the conductor at constant temperature. V is proportional to I and V is equal to IR, where R is the resistance of the conductor. Students, I have used a fan regulator to a bulb. So, usually at home when we turn the regulator on, we can increase the speed. Now, let us see what will happen to the bulb. As we are increasing the number, the resistance is decreasing, and look at the bulb how it is glowing. As we decrease the resistance further, more and more current flows and the bulb glows brighter. Once again, this is number 1. So, very little current is flowing, we are decreasing the resistance further, the bulb glows more brighter, and this is the full voltage which we are applying, that is the lowest resistance, and maximum current flows through the bulb. For Ohm's law, we have a triangle where you can find out whichever quantity is not known. When you want V, close V, we get the formula V equal to IR. If you want I, then close I, you get I equal to V by R. If you want R, close R, you get R is equal to V by I. With this triangle, you can find out the unknown quantity, and we discussed ohmic conductors which obey Ohm's law, and the conductors which do not obey Ohm's law are called non-ohmic conductors. The graph for current versus potential difference will be a straight line for ohmic conductors, whereas the graph for current versus potential difference is non-linear for non-ohmic conductors. The electrical resistance. Electrical resistance of a conductor is the measure of opposition to the flow of electric current through it. Conductors which offer considerable amount of resistance are called resistors, and those which offer very less resistance are called very good conductors, and those which have very high resistance are called bad conductors or insulators. Factors affecting resistance of a conductor. Resistance depends on the nature of the material, length and area of cross section. Greater is the length, greater is the resistance. Lesser is the length, lesser is the resistance. Greater is the area, lesser is the resistance, and lesser is the area, greater is the resistance. So, we can write resistance is directly proportional to length, and resistance is inversely proportional to area, and resistance is directly proportional to length by area. and series connection. We have discussed that whenever resistors are connected in series, the equivalent resistance is given by R1 plus R2 plus R3, or the sum of all the resistances in the circuit. When resistors are connected in parallel, the equivalent resistance is given by the equation 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. If there are more number of resistors which are connected in parallel, then we have to take the sum of all the reciprocals of the resistances, which gives you the reciprocal of the equivalent resistance. Children, let us discuss Kirchhoff's laws. Consider a wire in which a current I1 is flowing at a point A. So, we find current is equal to I1. As the same current flows in the wire, if you select any other point B, the current will remain same, which is I1. Now, let us say there is another wire which is connected to this wire at point P, and the current flowing in the second wire is I2. The current at B now will be equal to I1 plus I2. This is based on conservation of electric charge. Kirchhoff's junction law. The sum of currents flowing into junction must be equal to the sum of currents leaving the junction. Consider a junction where there are 6 different wires in which currents are flowing to the junction, and in some wires the currents are flowing away from the junction. Here I1 is flowing towards the junction, I4 is also flowing towards the junction, and I6. So, sum of all these currents must be equal to the sum of the currents which are leaving the junction, that is I2, I3 and I5. These 3 currents are leaving the junction. So, sum of currents leaving the junction must be equal to sum of the currents which are flowing towards the junction, that is I1 plus I4 plus I6 must be equal to I2 plus I3 plus I5. Let us consider an example. Here we have a junction where 2 currents are flowing towards the junction. So, in the third wire the current must be equal to I1 plus I2. Here we have another junction where I1 is flowing towards the junction and I2 is flowing away from the junction. In the third wire the current must be equal to I1 minus I2. Children, let us discuss Kirchhoff's second law, that is the loop law. Kirchhoff's loop law, which says the algebraic sum of increases and decreases of potential difference across various components of the circuit in a closed circuit loop is 0. Consider a network where we have resistance R1 connected to V1, resistance R2 connected to V2 and another battery V3 as shown in the figure. In this we can consider a loop which is A, B, C, E, F, D, A, or we can select a loop which is D, C, E, F, or a loop A, B, C, D. Kirchhoff's loop law holds good for any loop in a network. Let us consider another loop where there is a battery connected to a resistor. Let the voltage be V and current be I. In this we have to select any point, and from this point we will move along the network. When we move along the loop, we have to measure the potential differences and then come back to the same point, and measuring all the potential differences, the sum of all the potential differences must be 0. Here we have taken the potential difference across the resistor as negative. So, V minus IR is equal to 0. Children, when we have a little complicated network, it is very difficult to understand which is positive and which is negative. How to consider potential difference as positive or negative? We need to follow a sign convention. The sign convention is as follows. Whenever we move from high potential to low potential, consider the potential difference as negative. Whenever we move from low potential to high potential, consider the potential difference as positive. How do we know if the potential is high or low? For a battery, positive terminal is at high potential and the negative terminal is at low potential. For a resistor, current flows from higher potential to lower potential. Let us consider an example and apply Kirchhoff's loop law. Here is a network where we have resistance R1, battery V1, resistance R2, a battery V2 and a resistance R3. Let current I1 flow through resistance R1 and current I2 flow through resistance R2. Through the resistance R3, the current must be equal to I1 plus I2. This is from Kirchhoff's junction rule. Now, the potential at R1, we see that high potential is marked at R1 and low potential L is marked at R1. Similarly, mark low potential and high potential at V1 and high potential and low potential at R2, low potential and high potential at V2. Similarly, high potential and low potential at R3. So, after marking high potential and low potential points across various components, now let us write the equations. To write the equation, we have to select any loop and remember the sign convention. Low potential to high potential is positive, high potential to low potential is negative. So, let us select a loop A, B, C, D and we start from the point C. We move towards D. As we move towards D, we come across the battery V2 and we move from high potential to low potential. So, high to low is negative. So, we write minus V2 and then we come across R2 and we are moving from a low potential to high potential point and hence the potential difference across R2 is taken to be positive. So, the potential difference is I2 R2. As we move further towards A and then we come across resistance R1 and we move from high potential to low potential and hence the potential difference is negative, which is minus I1 R1 and further we come across battery V1 and the potential difference is from low to high and hence it has to be positive. So, plus V1 we have to write and come back to point C. Now, the sum of all these potential differences must be equal to 0. So, this is how we have to write the equation using Kirchhoff's loop law. We can consider another loop and we get the equation minus I1 R1 plus V1 minus I1 plus I2 times R3, which is equal to 0. Using another loop, we get another equation minus I2 R2 plus V2 minus I1 plus I2 times R3, which gives you 0. Solving any of the two equations, we can find out I1 plus. So, this is how we can use Kirchhoff's rules to find out the unknown values of currents in any network. Children, now let us discuss electric power. Electric power is the rate of electrical energy consumed. Power supply will do work in moving the charges for which energy is spent and this is equal to the work done in moving the charges. So, work done will be equal to V times Q. V is the voltage, Q is the charge. So, work done is equal to VQ and charge Q can be written as current into time. Substituting, we get work done is equal to VIT. So, power is equal to work done by time. So, substituting the values, we get VIT divided by T, T gets cancelled and power is given by VI. Applying Ohm's law, V equal to IR, we have power is equal to V square by R and I square R. SI unit for power is watt, that is 1 joule per second. Children, we have many devices used at home. Each device will draw some current and use some power, that is it will consume some power, that is it will consume energy, that is electrical energy every second. So, let us look at an example. A bulb is marked 220 volt and 100 watt. Calculate the current it draws and its resistance. We know power is equal to VI. The voltage is 220, power is 100 watt. Substituting, we get 100 is equal to 220 times I. So, current I is equal to 100 by 220, which is 5 by 11 amperes. So, 100 watt bulb will draw 5 by 11 amperes when given a 220 volt supply. Power is equal to V square by R, or R is equal to V square by P. So, substituting the values, 220 square by 100 gives you 484 ohm. The SI unit for power is watt, which is 1 joule per second, but in day to day life it is very difficult to use this unit to measure the amount of energy which is consumed, because it is a very small unit. The electrical energy which we consume has to be measured and then it has to be billed, which we have to pay. For this we use another unit called commercial unit, that is 1 kilowatt hour. Commercial unit for electrical energy is 1 kilowatt hour, which is 1000 times 3600 seconds, which is 1 hour, and 1 watt is 1 joule per second. So, substituting all the values, we get 1 kilowatt hour equal to 36 lakh joule. Children, in our homes we use many devices and all of them are connected to electricity. Have you ever wondered how they are connected, whether they are connected in series or in parallel? For this, let us do this activity. Here are two bulbs connected in series. Children, we have two bulbs connected in series. This is a 100 watt bulb and this is a 200 watt bulb. Now, let us see how a 200 watt bulb glows when full voltage is given. Now, the same bulb when connected in series with a 100 watt bulb, let us see how it glows. This is glowing much dimmer. This is because this 200 watt bulb has a lesser resistance and hence the voltage across this bulb is lesser in a series connection. 100 watt bulb has a greater resistance and hence this one will have more voltage in a series connection. Now, let us replace a 200 watt bulb with a 0 watt bulb. Now, this is a 0 watt bulb and this is a 100 watt bulb. Repeat, this has less resistance than a 0 watt bulb. Now, let us see what will happen when we turn on. We see that the 0 watt bulb is glowing more brighter than a 100 watt bulb. This is because this has very little resistance and hence very little voltage is here and more voltage is across 0 watt bulb, and hence 0 watt bulb will glow brighter. We connect all the bulbs in parallel. When we connect in parallel, we can turn on any device whichever you want. You can turn on all of them or individually one bulb at a time. The advantage of connecting in parallel is we can supply 220 volt to each bulb separately and we can operate any bulb whichever we want at our convenience. So, children, with this activity we have understood that all the appliances must be connected in parallel. Also, there is one important device which we use at our homes, that is fuse. In all the domestic electric circuits and also in industries, all the appliances must be connected in parallel. When all the appliances are connected in parallel, we can provide the same voltage to all the appliances as well as whichever device we want can be turned on while all remaining off. Also, there is a fuse which is connected to all these devices. Whenever more current is drawn by these appliances, the fuse will get burnt or blown off and the domestic circuit will be safe. Fuse is a device which breaks the circuit in the event of short circuit or overloading. So, this is the conventional fuse which we use, which has a fuse wire, and as its melting point is less, whenever more amount of current flows in the wires, the fuse wire will melt and will break the circuit. Nowadays, we have MCBs which are miniature circuit breakers whenever overloading or short circuit occurs, the fuse will just trip off, and after troubleshooting the error where the short circuit has occurred, we can turn the MCB on. Children, let us revise. Electric current is defined as the amount of electric charge passing through a cross section in 1 second. In case of metal wires, the charges are free electrons. Formula for electric current is Q by T and SI unit is ampere. Just like an object rolls down if there is difference in heights, electric charges move only if there is potential difference. A battery supplies electrical energy by maintaining constant potential difference across the wire. With the help of an electrolyte, a battery can maintain a constant potential difference. Ohm's law: the current in a conductor is directly proportional to the potential difference applied across the conductor at constant temperature. V is proportional to I and V is equal to IR, where R is the resistance of the conductor. Electrical resistance of a conductor is the measure of opposition to the flow of electric current through it. Factors affecting resistance of a conductor: nature of the material, length and area of cross section. Resistance is directly proportional to length and inversely proportional to area of cross section. So, R is proportional to length by area. Equivalent resistance of a series connection: when resistors are connected in series, equivalent resistance is given by the sum of individual resistances. When resistors are connected in parallel, the equivalent resistance is given by 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Kirchhoff's junction law, which says the sum of currents flowing into the junction must be equal to the sum of the currents leaving the junction. So, in this case there are 6 wires and 3 currents I1, I4 and I6 are flowing towards the junction, and I2, I3, I5 are flowing away from the junction. So, I1 plus I4 plus I6 is equal to I2 plus I3 plus I5. Kirchhoff's loop law, which says the algebraic sum of increases and decreases of potential difference across various components of the circuit in a closed circuit loop is 0. Electric power: the rate of electrical energy consumed is electric power, which is equal to VI. Also can be written as V square by R or I square R. The commercial unit of electrical energy is given by 1 kilowatt hour, which is equal to 36 lakh joule. Children, we come to the end of the chapter electricity, and I would like to request you all people to work out as many numericals as possible and observe various connections which are there at your homes, and also try to think whenever we are using electrical devices, what is the wattage, what is the voltage and what is the current it draws. Also take proper precautions whenever you are using electrical appliances. So, let us meet in another session with more interesting topics. Thank you.
చదువులమ్మ నేరుగా ప్రతి ఇంటి గడప చేరగా మీ భవితకే భరోసా దూరదర్శన్ వేదికగా. తెలంగాణ రాష్ట్ర ప్రభుత్వ సహకారాలే ఉండగా